Okay, so now we look at landing. So what happens in landing? Reverse of takeoff. You come from an obstacle height, touch on the main landing gear first, and then proceed. Now, there are many problems that can happen in landing. You can see one example here when the nose gear of the aircraft was not working. So there was a very interesting scenario in which one person used his truck. He positioned himself on the truck in front of the landing aircraft so that the aircraft could put the nose landing gear on the truck. Okay. So this is a very heroic thing. Now this is not what we want to do every time, correct? Obviously we don't want it to happen like that. So what do we want to happen is, you are coming in at some speed at landing. Again you have a screen height or the obstacle height. So this is the final approach, okay, and then you have a flare and then you have a touchdown. So the flare is the opposite of transition. It's now again a concave circle. So the distance from the obstacle height to touchdown is called as the airborne distance. In takeoff it's called as the climb distance. And after touchdown you are just rolling. So that is takeoff ground roll, TOGR, or TOL, takeoff ground roll during landing till you come to the stop. Okay, so the final approach is a steady descent. The flare is a curve. Float is one small point where opposite of rotation, you are touching the ground but nose is still up, so you slowly come down, that is floating. And then finally you have the roll. And after you actually come down, then you start applying the brakes and you have a ground run. So let's see, how do you estimate? This is actually much simpler. So it's just minus VA square by 2A, where A is the acceleration during coming into land. This is difficult to calculate. So some numerical values are given based on the braking system. I am talking only about the landing on the ground. So depending on various types of brakes, you can have different decelerations and you can use those numbers. So let's look at some interesting things. The landing distance will increase as wing loading increases. So again, from takeoff and landing, both we want to have low wing loading. Okay. Similarly, density. Landing distance increases as wing loading, wing density, not wing density, this is wrong, it's actually air density. So when the air density reduces at a higher altitude or hotter condition, landing distance increases. So these are the two important points. So now the question is, how to decrease the landing distance? Once again you need to create larger decelerating force. So one way is reverse thrust. So when you touch down, you can see the back of the engine, something has opened up. In fact, the air is now coming from there, you can see. The rear is almost closed. Another example on a 747. Look at the engine. Similar thing. Another example. This is what I had asked in the question, the first question that we gave. These are flaps which open and the rear is closed. So the air is now being thrown back or thrown forward. Notice they come on only after all the wheels are touching the ground. Okay, so this is reverse thrust. But while calculating the distances, we do not assume this is present. We ignore this. Why do you think we do that? Because? Yeah, because it may not be working. You cannot say, sorry, because the reverse thrust did not work, we had a crash. Not acceptable. Okay, so reverse thrust is as over and above the safety. It's the safety margin. The other way is arresting gear. This is the reverse of catapult. So the aircraft entangles itself into some kind of a cable on the runway, and you can see there is an energy absorbing piston which tries to absorb the energy. So in a 12-second cycle, the energy absorbed, you can see the damping force is so high. Another example is a drag parachute. This is also very common in military aircraft. There are some military aircraft in which drag parachute is compulsory. It is always used. Just like in some aircraft, the thrust reversal is always used. And also in some cases, afterburner is always used. So similarly, this is a situation where parachute is always used. And then we are all aware about spoilers. It's a very interesting video. At Mumbai airport during arrival, see the wing, how much it is vibrating. Touchdown, the camera is shaken and the soil has come out. This video was shot by me using my mobile phone when I was landing from Goa to Mumbai one day. So you can see how spoilers are working. Okay, so let's go ahead. Let's look at the flap settings during takeoff and landing. So flaps are used during takeoff and during landing, but there is a difference. In takeoff, we are more concerned about increasing the CL at takeoff so that we can have a lower takeoff velocity and therefore the S takeoff can be reduced. Okay. And if we increase the CL takeoff, there is a problem. CD also increases because CD is equal to CD naught plus KCL square. So if you increase CL takeoff, velocity of takeoff reduces, that is a good thing. So takeoff distance reduces, but at the same time CD also increases, the takeoff distance will increase. So there has to be a balance between the two. So we must have in such a way that the decrease in velocity is more than the increase in the drag during takeoff. So essentially what is important is not just CL increase or CD increase. What is important is L by D, lift over drag. So we choose a setting at which we get more benefit from velocity reduction and less problem from drag increase. Okay. So when you use the correct combination, you get the lowest takeoff run. This is during takeoff. During landing, so CL at landing, if you increase, then the approach speed will reduce. If the approach speed increases or reduces, this is not STO, this is S landing. This is a copy paste problem. It's S landing. And if you increase the CL at lift, unfortunately again the CD will increase, because again CD naught is equal to CD naught plus KCL square. So S takeoff is going to, so this is a benefit, both of them are beneficial now. So here there is no problem, there is no conflict. So what we will do, we will go for maximum possible in this case. Maximum possible means largest value, because the largest value of CL will give you both lower approach speed as well as higher drag. So generally the CL max at takeoff generally is approximately 80% of the CL max at landing, and CL max at landing is equal to 100% of CL max. So the aircraft always lands or tries to land at CL max possible with the best possible flap setting. So at landing CL equal to CL max, at takeoff CL is equal to 0.8 times CL max. So therefore the flap setting that is used for takeoff and landing generally vary between 20 to 40 degrees for takeoff and 40 to 60 degrees or even higher, 65 degrees also is common for landing. Okay. So that is the beauty. Now let us say we are coming in to land, but runway is not available. Many reasons are available, mostly because of weather, because of some problem at the runway. So the pilot is made to fly on what is called as a holding stack. These are oval paths above the airport or near the airport at which you have to maintain a particular height and a particular speed. Because there could be many people in one stack over the other. So these are typically used in the arrival, okay, at busy airports and at busy times at any airport. So to be able to have enough fuel to meet this requirement, there is a regulatory requirement of extra fuel for holding. And approach paths also can have a massive change depending on weather, depending on operating conditions. So one example I will show you. This is a screenshot from a pilot. So this is the usual flight path for a flight arriving at this airport. This is Houston Airport in Texas, USA. So flights which arrive from Europe normally come along that path. Okay. But because of bad weather, they may actually be made to travel extra 800 kilometers and come from this side, that yellow line. Incidentally, College Station is a place where I spent about 3 months, so that's why I just marked it there. Let me show you how, a very good example of a simulation. On one particular day, okay, lots of people were traveling to meet lots of their friends, etc. It's a Valentine's Day, and that caused a massive demand for travel, and coupled to that, February in UK can be very bad weather. So you see what happened on that particular day around 3 years ago, and you see the effect of that on the flight.
Unpredictable weather is one of the most challenging things for air traffic controllers to deal with.
This is UK.
The southeast of England is one of the busiest and most complex areas of airspace in the world to manage.
Landing stacks.
This day from 2014 shows how a severe storm can add to that challenge.
So there are three colors.
A day of strong winds,
blue color is the
landing
flights,
rates,
yellow is the delayed flights,
stacks
and red are the diverted flights.
Waiting to land. At 3 p.m, the wind suddenly changes direction and increases in strength, requiring a break in Heathrow arrivals to change the landing direction. As more aircraft arrive from Europe, the airspace becomes increasingly busy.
Holding stacks over Luton.
New holding stacks open as the skies become full of circling aircraft. By now, delays are touching almost 2 hours, with many pilots choosing to abort their landings and divert to other airports. Every diversion requires special attention and coordination to create new bespoke flight plans. thanks to the teamwork of everyone involved, every aircraft landed safely and without a single loss of separation, despite it being one of the worst days of weather in recent years.
NAT stands for National Air Traffic Service of UK, which provides the air service just like we have Airports Authority of India. Okay, so now we come to the last part, and that is the most dangerous part, that is takeoff and landing during crosswinds. Crosswinds are basically winds coming from the side. Okay. So one example, or let's look at this.
A pilot always tries to take off with a direct headwind. However, this very rarely happens. Almost always, there will be some crosswind component. Since crosswind takeoffs occur so often, it's important to develop this skill relatively early in your flight training. The correction required during takeoff is very similar to that required during taxiing. If the crosswind is coming from the left, the yoke gets pointed to the left. By doing this, the left aileron is deflected up, creating a downward force on the left wing and preventing that wing from rising too early. The opposite would happen with a crosswind from the right. When lining up on the runway, you should apply full aileron correction into the crosswind. Remember that as the airspeed increases, the controls become more effective. Therefore, as the ailerons become more effective, the pilot needs to reduce the aileron input. Otherwise, you'd be overcompensating for the crosswind. To keep the takeoff path straight down the center line, rudder force will also be necessary. This is because a crosswind condition will cause the airplane to weather vane, or turn into the wind. Remember that with a normal takeoff where there is no crosswind, you need right rudder. Now, with the crosswind, things change slightly. If the wind blows from the left, additional right rudder will now be required to compensate for the airplane's tendency to weather vane to the left. However, with a right crosswind, less right rudder will be required as the weather vaning tendency to the right will oppose the left turning tendencies.
I have a question. So why do you need a right rudder when you are not having any crosswinds? If you notice, he said that in normal takeoff, you will require a slight right rudder. And now if there is a crosswind from the left hand side, you have to put more right rudder. If there is a crosswind from the right hand side, you have to put less right rudder. Okay, let me show you to you once again. Listen carefully.
The normal takeoff where there is no crosswind, you need right rudder.
Why? In normal takeoff, when there is no crosswind, why do you need some right rudder? In a normal takeoff, you need some right rudder. Yeah?
Sir, might be because of propeller effect.
Yes, because the propeller throws air in one side. So the air hits the aircraft with a bias. Correct? So if you do not put right rudder, depending on the direction of the propeller rotation, you will have force on one side. So in the Europe and in the USA, you require right rudder. In Russia, you require left rudder because Russian aircraft propellers rotate in the opposite direction. Okay. So whatever the case may be.
Now, with the crosswind, things change slightly. If the wind blows from the left, additional right rudder will now be required to compensate for the airplane's tendency to weather vane to the left. However, with a right crosswind, less right rudder will be required as the weather vaning tendency to the right will oppose the left turning tendencies. As the airplane is accelerating down the runway, the relative crosswind component never becomes zero. Consequently, aileron input will be used throughout the entire takeoff. With improper crosswind correction, the airplane may begin to get pushed off centerline. This side loading causes stress on the landing gear, so it's important to use aileron correction throughout the entire takeoff roll. As the airplane lifts off the ground, the downwind wing and wheel should rise and lift off the runway first. If gusty winds exist, the rotation may be slightly delayed in order to allow the airspeed to rise, allowing a definite takeoff with...
Okay, so you got the basic idea. So let's see one example of a dangerous crosswind landing. Now, this video is scary for some people, so I'm giving you a warning. It's a real life situation. You can see it happened in Madeira in Spain just last year. So it's a very beautiful Spanish town. Coming into land, audio is not needed because there is nothing. You just see it's coming into land. It has crossed the runway and now it is turning. And just before landing, again there is crosswind. So now see, look at the right wing now. Okay, the pilot, and look at the runway, it's not straight. It's actually up, flat, and then down. So this particular airport is located next to a mountain, and there are some side winds or crosswinds, and this mountain system creates a complicated disturbance. So you are never sure about what will happen. So it's lucky that the aircraft survived, but you saw the way it went across the runway and then turned. It could have been very dangerous. Okay, there are more dangerous examples which I will show you in the next. So you can have three situations. You can have ideally no wind, or you may have a headwind, or you may have a tailwind. Okay, this is very good. This can be easily handled. And in all other situations you have a crosswind, and sometimes the crosswind can be more. So there is a typical requirement which says that an aircraft is allowed to land if the crosswind that it encounters is less than 1/3 the stalling speed. It's a rough rule, it's a thumb rule. So if your stalling speed is 90 knots, you can land in 30 knot crosswind. If the crosswind is 50 knots and Vstall is 90 knots, you are not supposed to land. You are supposed to abort the landing, as we will see in some examples. Okay. So how do you calculate the crosswind value? You use a chart like this. Okay. So you look at the angle between the wind direction and the runway that is given to you by the air traffic control authorities, that when you are coming into land, there is a crosswind coming at 70-degree angle. So this number is known to you. Okay. Let the wind velocity be 30 knots, so you have this 30 knots line. So where it meets 70, you just drop a horizontal, drop a vertical line, and that gives you the crosswind. If this value is more than 1/3 your stalling speed, chances are you cannot be allowed to land. Okay, this is how it is calculated. Okay, now let's look at vertical takeoff and landing, for which there are examples available both from either a tilt rotor like this. Can you identify this aircraft? Which aircraft is this? Nobody knows? So you can't name that aircraft? The previous one? What is it called? This is the one, but what about the previous one? V-22 Osprey. Look at how it operates in vertical takeoff mode. Let's see it once again. So look at number 1, number 2, and number 3 will be the nozzle. So 3 things have to be deflected. First thing that you saw is opening of the canopy for the lift engine. There is a dedicated engine in the front. Notice how the 2 horizontal tails are fully bent down, full deflection. aircraft is almost stationary, coming down at a very low speed. You can now see the mechanism, how it is done. So this aircraft has a dedicated lift engine. Okay. This lift engine sucks the air from the top and throws it down to give you one force, and then there is a nozzle in the middle of the engine and the exhaust also is bent down. So it rides on 3 legs. And there are actually 2 more on the wings for giving lateral support. So there are basically 3 plus 2, 5 jets on which it sits. So why not use in personal aircraft or in transport aircraft? It would be fantastic, right? You can take off from IIT Bombay and go to IIT Kanpur and land, if it is permitted or if it is available. So why is it not there? There are many reasons for it. The first reason is extremely high consumption of fuel. Then there are safety issues. You saw one trial, but there were many failures before this actually succeeded. Then there will be huge noise levels which are okay for military aircraft but not for conventional aircraft. If we provide it, the cost per person will go up so much that you will not be able to afford it. And secondly, this gives you a very low speed. So because of these reasons, we don't normally see this in personal or transport aircraft. So this we have seen so many times, what happens if one engine fails. But if you look at what happens when one engine fails in this kind of aircraft, the consequences can be disastrous. So here is one example of an engine failure during the takeoff. This aircraft has a very unique record. It is the aircraft that took the maximum time for design and development. No other aircraft in the world has taken so much time from conception to testing to finalization. The amount of time needed by this aircraft was a world record highest. So I want you to tell me on Moodle page, how much is that time? How many years did it take for this aircraft from conceptualization to certification? Okay. Now let's look at what is in store in the future for landing. This is a project, it's a research
European research project to improve aircraft efficiency by elimination of the landing gear.
No landing gear.
Efficiency is all about optimization, and it's not that easy anymore. In pursuit of the best economic performance, much has already been done before. More progressive weight reduction is a clear way forward. For instance, a fair amount of weight could be saved by removing the landing gear from the aircraft. Wheels may be useless while airborne, but need to be substituted on the ground.
Around 6%
Let's have a
weight
look
can be
at a
saved.
possible workaround. Gabriel features a ground-based cart and a magnetic sledge to support taxi, takeoff and landing. Conventional runways would be substituted by a magnetic track. Instead of wheels, aircraft would be equipped with a harpoon system to establish safe connection to the cart. Now let's see Gabriel's vision of the magnetic takeoff. The sledge would levitate above the track using a vectorable magnetic force. When set forward, this force will support acceleration, reducing the need for engine power. This will result in lower noise levels and emissions. In other words, greener operations. The excess power available for takeoff will create a new opportunity for smaller and therefore greener engines. The magnetic levitation system will be electrically powered and thus can be better served by renewable sources. Reaching takeoff speed, the cart will follow the liftoff sequence. Harpoons will be unlocked at the right moment. Once decoupled, the sledge will stop and return to its original position. The harpoon of the departing aircraft will be retracted, just like conventional gear struts. Improved energy efficiency will also allow for steeper climb and shorter runway tracks. But how do you land an airplane without wheels? Well, this is all about proper synchronization. The acceleration of the sledge must be precisely controlled. A reliable high-speed data link will take care of the automated synchronization process. Precision is crucial. By the time the aircraft reaches the flare position, the sledge must be right underneath without any difference in velocity. Moreover, speed is not the only parameter to be synchronized. At the moment of touchdown, different aircraft's angles of attack may vary. Not to mention the longitudinal slippage phenomenon of landing in crosswind conditions. At touchdown, the aircraft's harpoons will be locked tight by the fifth wheel style cradles of the cart. Energy dissipation will also be assisted by the maglev track, resulting in more efficient braking. It is of course obvious that without wheels, aircraft ground movement has to be assisted as well. To facilitate ground taxiing, the cart will be decoupled from the sledge, and with the help of its own electric motors, it will move the aircraft around the airport. The maglev runway is a high-level concept, but the early experiments are promising. This, along with the magnitude of the potential benefits, qualify Gabriel for further research.
Okay, this is about the future. There are many benefits. Okay, and I want to end with this very beautiful video of a vertical takeoff in a transport aircraft. So how the hell is it possible for a transport aircraft to take off vertically?